Presenting data online is no easy task. In fact, presenting it anywhere is no easy task, especially if you want to make it engaging, interesting, and even a little bit innovative. There are plenty of libraries out there, but what if you want to take it to the next level? Well, you're going to love our next session if that's the case. Taken to the stage for the 2021 CityJS conference is KRYSTAL from Montreal in Canada. KRYSTAL is a senior front-end developer at Shopify, and in this talk, KRYSTAL will be exploring how you can take your data visualizations to the next level. There are plenty of libraries out there which can get you started, but if you want to craft something which is truly amazing, you're going to need the tools to build something from scratch. Thankfully, KRYSTAL is here to help. Don't forget to keep your questions to one side and join us for the Q&A session, which will be starting straight after this talk, as well as keep posting on social media using the hashtag CityJS2021 and keep those comments rolling in wherever you're watching along online. KRYSTAL, it is my pleasure to invite you up to the conference stage.
Hi everyone, I'm KRYSTAL and I've been working as a creative coder for about 12 years now. During this time, I've had the opportunity to do a little bit of everything from web and mobile application development to 3D modeling, games, and VR. I'm also part of the Insights team at Shopify, where we create awesome data visualization experiences together. Today, I'll walk you through some of the techniques that I've learned along the way so that you can create your own reusable and performant React experiences. But before we actually start talking about code, I always like to cover this topic because I think it's important. Motion is a message. If you think about it, in real life, things don't, just pop in your face. It would be really scary if they did. Instead, what happens in real life is that things move from one place to the other, like this furry monster walking in real life from one side of the screen to the other. The thing about motion, though, is that when used wrong, you can actually make the experience worse. So let's have a look at one example. Like almost everyone, have been obsessing over COVID-19 data since the beginning of the pandemic. And because I live in Canada, I always come across this one from a Canadian newspaper. You will notice that when we switch from total to breakdown, the total yellow area slides down as the breakdown areas slide up. This makes it really hard for my brain to understand what the relationship between the layers of the breakdown and the total is. It should be clear that the breakdown represents some layers that sum up to form the total. But because everything is moving at the same time, it seems like both of the data sets are not related at all. So let's compare it with an alternative. Here, when switching between total to breakdown, only the breakdown layers slide up and down. The total stays there. This makes it easier to understand, but to be honest, this is a perfect example of when using fancy animations is not ideal. So let's have a look at one final alternative. Here, when switching between total and breakdown, we have a simple fade that reveals and hides the layers of data. This is great because it makes it obvious that these layers sum up to form the total. My brain does not have to follow some lines moving randomly around to try to understand what's going on. It's just there. There are, of course, lots of situations where motion can improve your understanding of what's going on. So let's have a look at another example. Here, we have a chart that compares the number of sales from this year with the same period of last year. We can choose which period we would like to compare. This week, this month, or this quarter. Notice that when we are comparing this quarter to last year's quarter, the line is red because the total number of sales in that quarter was lower than last year's. But when we switch to this week, the line becomes green, as this week, compared to the same week last year, had more sales. The animation here helps us understand where things live in a timeline, because the data point, the range that we are choosing lives in a timeline, and zooming in and out of that period, the animation helps us understand what's going on. Another example. This chart shows the number of page views in the last 10 minutes. So we have 10 bars, one for each of the minutes. What is interesting here is that the bar for now keeps growing as it receives more data until the minute is complete. When the minute is complete, another bar appears and push all of the bars to the side so to make way for itself, helping us understand what's going on. So that's enough talking. Let's dive into the code. But let's start with a really quick 2-minute SVG refresher. So SVGs work in a way that is pretty similar to HTML. We can work with an SVG by defining an SVG tag that contains a view box. That view box is kind of like a window for looking into the SVG world. And SVGs use a coordinate system, an X and Y coordinate system that goes from left to right and top to bottom. And the view box, those two first numbers there are the X and Y coordinates for the origin point, marked here with the red dots. And then we define a width and a height for the view box. Inside the SVG, you can define multiple tags for different shapes, like a polygon, for example, where you can pass in a sequence of points. Those points are X and Y coordinates for the vertices of the polygon, or rex tags that you can use to create rectangles. It works pretty similar to the view box by defining an X and Y origin point, and from there a width and a height for the rectangle. Or circles that work slightly different because the origin point is in the middle. So you pass in CX and CY to mark the center of the origin, and then a radius to define how big that circle should be. And finally, we have paths, which are by far the most powerful way of creating shapes in SVG, as you can use paths to create any of the other shapes that we talked about so far. That sequence of letters and numbers that you see there is basically a sequence of commands. So imagine that you're holding an imaginary pen on top of the SVG, and that sequence of numbers and letters is telling the pen to move to XY, then draw a curved line to XY, then a straight line to XY, etc. Thankfully, there are lots of programs that you can use to automatically generate the path sequence for you, like Inkscape, SketchUp, Illustrator, etc. And if you'd like to deeply understand how paths work, and I highly recommend you to do so, and we'll see an example of how that can be useful, I recommend you read this really nice article by Jacob Jenkov that you can find on this link, bit.ly/svgpath. The thing about these programs, though, is that they tend to generate code that is horribly messy. So you will want to run it through an optimizing tool to turn something like this into something like this. And for that, you can use the command line tool svgo or its website version svgomg. Now that we've covered the basics of how SVGs work, let's go through an example of dynamically modifying a path. Here we have an SVG path that represents a progress bar divided into steps. When a step is completed, a green line appears to fill how much of the total length of the path the completed steps represent. Doing this with a rectangle would be really simple. We would just need to change the width of the green bar to whatever percentage the completed steps were. But since we have that little curve in the end that connects to the flag, we can't actually use a rectangle for that. Instead, what we can do is access the path DOM element with the useRef hook, use the getTotalLength method on the path to get its length, use a little bit of CSS magic to combine stroke-array and stroke-offset to create a dashed path that only has one single dash, with the length of the percentage of the completed steps compared to the total length of the path. This is nice and all, but this is what happens when you resize the screen. You can barely see the progress line there when we're looking at in a small screen size like a mobile phone, for example. So that's not what we want. What we want is for the progress line to shrink horizontally but maintain the overall height of the SVG, so that this would work regardless of the screen size. For that, what we can do is analyze what that SVG path that was generated from Illustrator actually gives us. So remember that paths work like a sequence of commands to draw on the SVG space. So in this particular path, we have M, which stands for move to x0y76. And notice that this is an uppercase M, meaning that the coordinates are absolute. All of the other letters in the sequence are lowercase because they will always refer to the previous coordinate. In the second line, we have H, which stands for a horizontal line with 1100 pixels. And then we have C, S, and S, which are curve commands. And finally, a last L command for the straight line that connects to the flag. Now that we know what each command is doing, we also know that the part that we want to make dynamic is the horizontal line there. So instead of it being a fixed 1100 pixels, we want it to be the SVG width that will change according to the screen size minus 100. Because the 100 pixels will be reserved for the flag and the little curve that connects to the flag. Lastly, we want to make sure that the view box of the SVG is also being updated to match the SVG width according to the screen size. Awesome. So let's have a look at a more complete example so that we can start plugging in Z3. Recently, we were exploring how to represent the customer's behavior data of people accessing Shopify stores. This was our initial draft. The idea is that we would have all of these particles moving around in buckets for people with active carts, checking out, or that already purchased something in the last 10 minutes. It would be super cool if we could see all of those particles swimming in there and jumping from one Petri dish to the next one as people went through the sales funnel. The problem was that we could not actually track what each individual was doing. Instead, the data that we could get for this component looked something like this. As you can see, we only have a number for each of the buckets. No way of knowing which of the little microbes jumped from one Petri dish to the next one. So maybe we could implement the animation of the microbe jumping to a bucket from a random direction when the number increases. This could work, but it could get really messy really quickly if we have hundreds or thousands of people accessing a website. I mean, this looks kind of cool, those 3 evil blobs floating around, but it doesn't actually help me understand how many people are at each step or how the flow is going. So this was not going to work. This was our second version, and I think it's much, much better because we have 3 circles with different sizes that are easy to compare, so we can quickly know if we have more people with active carts, for example, or people that already purchased something. We can make it work with our data as well. Let's say that the first time to receive the data, the total checkouts is 15. Then the next time we receive it, it's 17. We know for sure that the number of people in the checkout incremented by 2. So we can trigger an animation for 2 running dots going from the active carts bucket to the checking out bucket. And we can do the same thing if the number of purchases increases. So let's see how we can use SVG and Z3 to implement that chart with React. We talked a lot about SVGs, but the cool part is Z3. And even though Z3 is cool and all, and we've all seen all of those fantastic examples of what can be created with it, it can be difficult to know where to start. I mean, this is a screenshot of Z3's API reference from their GitHub docs. Look at the size of this thing. Z3 is a really complete tool, and it has all sorts of methods that you can use to treat data, bind it to the DOM, etc., etc. But since we're using React to do all of the DOM manipulation for us, we should define what we are not going to use from Z3. And that would be things like Z3 selections. This module works in a similar way to what you would expect from something like jQuery, by selecting DOM nodes directly and transforming them based on the dataset. We do not want to use this module as we'll be letting React do what it does best. Take care of the virtual DOM in a performant way, and instead we'll use Z3 for what it does best. for being a toolbox to help us with math utility functions and layout calculations. So no Z3 selections. A perfect example of the kinds of things that we are going to use is Z3 scales. Scales are functions that map from an input domain to an output range. So if we look at an example of that in code, it would be something like this. We have an input array with some sample data. We can use Z3's extend function to extract the minimum and maximum values of that array, in this case 0 and 500. And we can then use the scale linear function to map those values to pixels so that we can render the elements representing the data in the screen. Z3 scales functions actually return a new function that we can call to convert values from our input array to pixels, in this case, or to the value that we're mapping. For example, to render the circles in the screen, we can use the function to get the CX position for each circle. So the first time that we pass in 0, we retrieve 0, and then we pass in 250, we get back 170, and then we pass in 500 and get back 330. So going back to the customer behavior chart, now that we know how scales work, we can explore how to change the size of the circle by using a Z3 scale. The first example that we saw was a linear scale, but using linear scales for calculating the radius of a circle is not the best because we humans, we tend to interpret the area of the circle to be the reflection of the value. So instead, we should use a scale square root so that the area reflects the value and not simply the radius. We can then use the radius scale to calculate the radius of each circle depending on the data. This is nice, but we are not animating the radius changes yet, so it doesn't look so smooth. Let's fix that by plugging in React Spring. We first import useSpring animated and config from the package. Then we set up an animation with the useSprings hook. It works kind of like this. The first argument is the number of springs or animations to create. The second argument is a list of objects describing each animation. It is here where we tell React Spring what properties it should watch for changes in order to animate. In this case, it's the radius property, where we're using the radius scale to get the value based on the data point. The config here is what defines the characteristics of the animation based on Spring physics. Things like mass, tension, friction, etc. Config.molasses is just one of the defaults from the package. If you'd like to read more about how Spring physics work, I highly recommend you read Josh Kumo's article, A Friendly Introduction to Spring Physics, that you can find on this link, bit.ly/springphysics. Once we have the radius springs prepared, we just have to render it. For that, we replace the circle tag with an animated.circle tag. And instead of calculating the radius directly, we get the radius from the radius springs. And finally, we can implement the running dots animation when we fetch new data. Similar to what we did with the radius, we'll implement the animation with the useSprings hook. To define the number of dots that should be rendered on the screen, we should be able to track the data changes. And for that, we can use a usePrevious hook, a custom usePrevious hook for that. Now that we have a way of keeping track of the value when it changes, we can observe changes in our data using a useEffect hook that has data as a dependency. Inside that hook, we'll check the count if the count has increased before doing anything else. We then calculate the increment size by comparing the current count with the previous count. This increment will be used to define how many running dots we should render on the screen. The animation happens quite fast though, so we can't really tell the difference once the number of running dots is too big. It's easy to count when there's like 1, 2, 5 running dots, but when it's a big increment, things like 100 or 200, you can't actually count them. So we can take advantage of that for a quick performance gain. Since we can't tell the difference, we can clamp the increment to never be more than maximum circles per bucket. Then we create an array of objects that we will use in the springs animation. By using the array method and passing in the increment size, we create an array of the length of our increment and fill it with objects that describe the animation. There's a lot happening there, so let's have a closer look. If you create an array by using an array method and passing it a number, it will create an array of empty cells that has the length that you provided. You can then use the fill method to fill it with whatever you want. So this could be nulls, it could be strings, or in our case, it could be objects. Each object will be the same. From CX, where we store the initial position of the running dots when the animation starts playing. In this case, it will start inside of the checking out bucket. Then a 2CX, where we store the final position of the running dots in the animation. And in this case, it will be the dots inside of the purchased bucket. And lastly, a radius. But remember that we talked about not being able to notice a difference if there were the big increment or not. We needed another way to signal when the increment was big or small, so we decided to change the radius based on the increment size. And that's exactly what this method does. If the increment is big, return a big radius. If the increment is small, return a small radius. Finally, once we have our array of objects created, we can actually implement the animation with the use springs hook, similar to what we did before, but there are a couple of differences. The first thing to notice is that we are applying a delay to each of the dots based on its index. If we didn't do that, all of the dots would run at exactly the same time and they would be on top of each other, so we wouldn't be able to actually see them. We would only see one dot at a time. By applying that delay, we create a trail effect, like if one dot was following the previous one. Then, instead of simply animating a value every time that it changes, we are defining where the animation should start and end with the from and to objects. Each of the properties inside of the prompt from and to objects will be animated. Here's how it looks in the end. A small radius for small increments. The radio bucket's radius also keeps changing as the number changes. And if we increase the increment size, the radius of the running dots is much, much bigger. Yeah. SVGs use what we call a retain mode API, meaning that we can always refer back to what is being rendered on the screen because we have access to all of those tags that live inside of the SVG. This makes it super straightforward to animate SVGs because we just have to update the properties inside of those tags. If you have to implement something that has a huge amount of animated elements though, you will start to notice that the more animated elements you add, the more to the DOM, the more the performance will drop. That's when we should use Canvas. The main difference between Canvas and SVGs is that Canvas uses what we call an immediate mode API. This means that there's no way of keeping track of what objects are currently on the screen, like we did with SVGs. Instead, it works like if we had a literal blank canvas and a paintbrush. You can give commands to the paintbrush so it draws on the canvas, but once it's there, you can't move the paint around. So you might be thinking, how on earth are we going to animate things then? And to answer that, I'll ask you to think of one of those paper flip books. I used to love creating them when I was a child. And animating HTML canvas is pretty much the same process. Since you can't actually move things around, you have to redraw each object in its new position at every frame. So going back to the customer behavior component, if we were to re-implement it with Canvas, we would use a animated.circle. We wouldn't use an animated.circle anymore. We would clear the whole canvas and then redraw each circle at the new position at every frame. Let's have a look at a simple example first. Suppose we wanted to have a circle moving from right to left on the screen. We could once again have a use spring hook to update the X position. We could even render the X position using animated.ziv. But the animated.zip, the animated that we import from the library, though, can also be used to create custom animated components. So in this case, we would have a canvas component that receives an x value as a prop, and then redraw the canvas every time that the x value changes. So in the first lines there, we have a reference that we can use to access the canvas element, and then we can get the 2D context of that canvas by accessing canvasref.current. The context is what contains all of the methods that we'll be using to draw on the canvas. So we can save it to a CTX constant so it's easier to access it later on. After that, we have a useEffect that keeps track of changes on the X value. And inside of that, a draw method that clears the whole canvas with the clearRect method that accepts an X and Y origin point and a width and height for how big that rectangle that is being cleared is. In this case, we want to clear the whole canvas, so X and Y is 0, and the width and height will be the same as the canvas. After that, we call context begin path, begin a path, which is pretty similar to SVG paths, but here we have more explicit names for the commands instead of just letters in a string. We then call context.arc to create a circle. You can use this method to draw circles or Pac-Man style arcs. So that's why it takes so many arguments. X and Y coordinates for the origin point, radius, start angle, and angle. And lastly, if it's anti-clockwise or not. Everything we did up to this point created an invisible path on the canvas. We then need to set a fill style with the color of the circle and then paint it with context.fill. Finally, we export the canvas as an animated canvas by using the animated method that we imported from React Spring. Once we have the animated canvas, we just need to import it to the parent component that has the useSpring hook and pass down the X value the same way that we would do for an animated.zip. So we could do the same thing in the customer behavior by passing a radius spring and the order running dots that we created before to an animated customer behavior component, canvas component. The Canvas API is pretty verbose though, so let's make our lives easier by introducing a couple of utility functions. So a draw circle that, draws a circle in the X and Y coordinates that we give, a draw rect that we can use to draw rectangles on the screen, and a clear canvas that clears the whole canvas. With these utilities in place, we can go ahead and include an useEffect hook that gets called every time bucket radius or the running dots array changes. The order that these methods get called also matter. We first clear the whole canvas, then we draw each animated element in its new position, and finally we draw the static elements on top of everything. Because in this particular case, we want the line that connects each of the buckets and the little dots in the center of each bucket to be on top of everything else that is moving. What the draw animated elements does is map through each of the radius values of the bucket's radius array we got as a prop, and use the index to determine the X position of each circle. And the Y position for all of them is going to be the same. We can then use a create radial gradient method to create an empty radial gradient in the position of each circle, and then choose a color to fill it with, because the last bucket is green, but all of the others are gray. The add color stop method basically creates the color stops in the gradient. We can then draw each bucket with the draw circle method that we saw before. And lastly, we do the same for the running dots. Get each dot CX, fill, and radius, and then use the draw circle method to draw them on the screen. Lastly, note on accessibility. Even though animations are super cool and many times they do help us tell a story, it can also be a horrible experience for people that are sensitive to motion and can get dizzy by seeing things move around on the screen. Many operational systems allow users to turn on a reduced motion option to help with this dizziness. In our project, we have a user-reduced motion hook that takes advantage of window.matchMedia to check if the user prefers reduced motion or not, and returns true or false accordingly. This plays really well with React Spring because it accepts an immediate prop that, when set to true, goes immediately to the last step of the animation instead of playing it. So basically, by disabling the animation. All right, so thank you so much for following along today. If you have any doubts, please do reach out to me on Twitter. As I mentioned before, my username is CAMPIONI. And we are hiring. So we will hire 2021 developers in 2021. If you'd like to come work with us, feel free to reach out to me directly or visit Shopify's career website.
Crystal, what a fantastic talk. Thank you very much for delivering that as part of this year's CityJS conference. You really were not kidding when you said you were bringing some next level data visualization to the CityJS conference stage. Fantastic stuff. I'm sure everybody watching along at home will be joining me in giving you a huge around the world round of applause. If you have any burning questions for Crystal off of the back of that talk and data visualizations using React, Spring and D3 more generally, why not join us for the Q&A session, which will be starting over on GatherTown any moment now, or post along on Twitter using the hashtag, yes, you guessed it, CityJS 2021, as well as keep those comments rolling in on YouTube.